All right, it is 9 o'clock. I'm starting the stream already. Um, just need to move the browser over a little bit. Yeah, need it. Okay. All right. All right, so let me put on my old person clip on. And what we'll do today is the first thing I'm going to do is to give you the solution of the lab on the other day so that you guys have an idea of what it is supposed to look like. I think most of you got it, okay? But if you want to confirm that your solution is indeed the correct one, we'll do it right now. And then after that, let me show you Joplin because I got all the lesson plan and whatnot in Joplin already. That's one of the reasons why I like using Joplin is I can keep track of what I need to talk about in the class. And it is nice because I can also use checkboxes. So this way, once an item is done, I can check it off and move on to the next one. All right, so the first thing I need to do today is to go over the previous lab, the one that was on Tuesday. And I'll give you a file. You can choose to use my file as a starting point of today's lab, or you can choose to use the one that you produced, on the other day. It is up to you. Are there any questions before we proceed with this exercise? Nope. All right, cool. All right, so let me go ahead and get started with Logisim. Actually, I might want to show you the command line here just so that you guys can see it. So java-jar, and then this is the home folder in Linux. If you're using Windows, it's a little bit different. But since the first week, I already gave you guys the instructions to use Windows instead of Linux. When it comes down to the command line, and then we just start Logisim. There we go. It obviously has to start on the wrong screen, so I'm going to put it into the right screen. Maximize. All right. So the first thing we need to do is to create the X, Y, and K0 as input pins. So this is going to be my X input pin. We'll call it X. It has 3 bits. It's 3-bit wide. And I duplicate it to become Y. So the name of a pin is not really that useful other than just kind of giving you an idea of what it is. And I think some of you might have used, the pin under wiring, this one, instead of the top one. The difference is if you use the one that I'm using, it does not have 3-state turned on automatically. That's the main difference. If you have 3-state turned on, then it doesn't actually have a value. Instead, it would display X, and then the gates won't like it, because it is not a specific value. So this is going to be my K0. So these are the input pins. And then from the input pins, I created tunnels. So the tunnels are just like that, and that, and one more. So tunnels are not 100% necessary, but they do help to make the code look, or not code, but to make the circuit look a little nicer. So that's why, I personally like to introduce the use of tunnels. And the tunnel has to match the width or the data bits of a tunnel has to match whatever it connects to. So now in this case, we have this one matching to X. Now the label of a tunnel is significant. In other words, every tunnel of the same name are logically connected. So that's why tunnels are useful because this way you can bring one particular wire or one particular conductor from one side of the circuit to all the way to the other side without drawing these long lines that would have a tendency to intersect with each other. But you can also see the name of a tunnel and the name of a pin. They are not associated. Okay, there's no automatic association between the pin and the tunnel, even though they have the same name. So in this case, if I want these two to be connected, I still need to draw a wire to have them connected, like so. All right, so next thing I think in the description is I gave you 3 tunnels as the quote-unquote outputs. So let's go ahead and make more tunnels here. One is called P, one is called G. So I'll just do a duplicate here. And then the last one is Q. I cannot remember the order, but it doesn't really matter because what does matter is do you remember what P, G, and Q are representing in the material that we have introduced so far in this class. So that boils down to whether you have read the modules, taken notes in class, and try to put all the definitions and all the symbols into one place so it's easy to look up. So this is the stuff that I have been preaching like from day one, and I'm hoping some of you are starting to have a habit of marking all the definitions, putting everything in one single spot, and also reviewing the material when you have the time. All right, so now we're gonna take these 3. So this is my lazy way of doing things. Duplicate everything, and then change all the facing at the same time to east. So this way, it's just it's one trick that you can do. All right, so now we need to draw the gates, right? So all the gates are 3-bit wide, and for the gates, we can go ahead and pick it out from here. And this is also how you can find out which one is an AND gate, which one is an OR gate, and which one is an exclusive OR gate, because they're all kind of documented here. So we're going to pick out an AND gate, we're going to pick out a OR gate, and we are also going to pick out an exclusive OR gate. And I'm going to do the same trick that I did earlier. I can now select all 3 gates. And if you look at the selection, everything that are common between all these gates are shown here, so I can make changes at the same time. So I'm going to change all of them to be 3-bit wide. I can change all of them to only have 2 input pins. And I can also now change all of them to use the narrow format instead of the usual medium format. So that just saves me time. So now I can put these things here. You can rearrange the gates if you want to. They do not necessarily have to follow the locations, as I indicated. Only the input pins are important when it comes down to the location. So now the question is, which one goes where? And since I am allowed, I mean, you guys do not need to move them around, but I'm just making it so that it's aligned with the tunnels. So P is the OR between the X and the Y. So that's why I put it here. G, oh, okay, that's because the tunnels have not been modified to have 3-bit wide. So that's what we need to do. And it is supposed to be changed now, but it's not taking it. So sometimes Logisim also has its own problem. There we go. This one goes here, and then this one goes here. All right, so all of P, G, and Q are derived from X and Y. So I just need to make sure that X goes into the input of every single gate that I have in this diagram, and then Y goes to the other gate, the other input of every single gate as well. And now we have P, G, and Q all done. So this part here, basically relates to the lab that you did last Thursday, which is the multi-bit gate lab. So that's basically the purpose of that lab, is to set you up so that you understand what is a multi-bit gate and how it is going to be applicable in this case. So the next thing we need to do is to create the subcircuits, K1, K2, and K3. So that means we need to go to project and then say add circuit. The first one is K1, and if I need to go back to the to my notes to find out how those circuits are supposed to be drawn. So right here we have K1 looking like this. So what I'm going to do something that's really lazy, which is to go to the clipboard, go to the text commands, and copy that. And then on the other side in Logisim, I am just going to paste it as text. So this way, I can, actually it doesn't work. For whatever strange reason, it doesn't paste, whatever is in the clipboard. Let me see. Oh, I got a better tool to do this. Okay, this is really kind of interesting. It is a Linux tool, but you can probably do something like this in Windows. All right, so I'm going to use my um, screenshot tool and just kind of cut out the portion that I need. So right now I just need this portion. So instead of doing all of this stuff here, instead of copying to the clipboard, I can open it with a tool, so I can basically just display it on the screen here. And you might say, but that's going to go away as soon as I switch to another window. Well, I can do something like this. I can make it always on top. So this way, no matter what other window I'm changing, this is always going to be on top. Unfortunately, I can't seem to move it. All right, so let's move and stash it here. And now we can switch back to Logisim and keep an eye on, the equation. I hate to put it this way, but, I am really, really bad at, remembering, equations, from one screen to another. And because, I want to limit the projection to a 720p resolution, so I can't really put too many different windows, onto the same screen at the same time. All right, so it's time to make the input pins. So there are two input pins of the same width. Both of these are 3-bit wide because they are representing the P and the G bits. And then the third one is K0. So that's a single bit. And now we need to label these. Now the labeling is not super duper important. It is just kind of important because I need to know which one is which one. And then the other thing that is also important is the location of the pins, the input pin and the output pins. So I really need to make sure that P is on top, oh, that's not Q, this is G. G is in the middle, and then K0 is at the bottom. Because otherwise, when you look at the appearance of the circuit, those ordering of the pins would be, they would be out of order, and that's not going to be good. All right, so we do need one output pin, which is our K1 in this case. So I'm going to label that as K1. So now the question is, what are we going to do? We need one AND gate to AND the P0, K0, and then out of that, we need to take the output of the AND gate and OR that with G0. These are 3 bits. So are these. So you need individual bits. And the best tool to extract the individual bits out of a wire, a multi-bit wire, is a splitter. So we look at this splitter, and just to be lazy, I'm going to turn it into a 3-bit wide, but also having a fan out of 3, because it is perfectly okay if you have too many split ends and you just not end up using all of them. It's okay. It just looks kind of ugly, but there's nothing wrong with it. So I'm going to split one more time, for G in this case. And now I have all the bits that I need. So according to this equation, I need an AND gate. So I'm going to put an AND gate here and change it to narrow and only have 2 inputs like so. And I need to AND P0, K0. All right, so that's, it's just a matter of, how you want to align everything. So I'm just going to align it like this, where K0 goes into one end or one input of the AND gate. And then we also have P0, which is right here. So this is also important, is every single thing in the equation is a single bit. We are not taking all the bits from P, we are not taking all the bits from G. We are designating bit 0 from P, bit 0 from G. So that's why the splitter is really important. So these two are ANDed together. G0 is all by itself going to the OR gate, which is not here yet. So I need to make an OR gate, same thing, go to narrow, 2 input, and there we go. So there we go, that's one. And then here's the other one. And then here's my output, like so. And it's done. So K1 is now done. I can test it right now, but I don't really have to, because I'm fairly sure this is right. But it is important to check the appearance just to make sure that it looks like this. Now, some of you, somehow, ended up with an appearance that is not like this. I have no idea how that happened. Um, it's possible it's a bug in Logisim, but I have not have the appearance, going in some weird shape at all. So I'm not really sure what's happening in those cases, but so we have P, G, and K0 as my inputs, K1 as my output, and it's just a matter of moving these labels to the right place. And once again, this part you do not need to do because it really is just for my own documentation purposes. So I know which end is which end, and this is just computing K1. And now we have K1 done. Time to move on to K2. So go to project, add circuit. This time we're adding K2. So we go to K2. It is completely empty. So this is also where I can be a little bit lazy by copying and pasting. So I just copy, Control C, go back here and do the paste. So all the connections in between, most of the connections in between, I probably need to remove those. So I can just go ahead and remove a lot of the wires in between. So get rid of that, get rid of that, get rid of that, and possibly get rid of that. And obviously this is no longer what I need to focus on. So now I do the same trick, but this time I do it to K2. I saw yesterday, or I should say on Tuesday, that some people embedded the K1 circuit within the K2 circuit. That defeats the whole purpose, the entire purpose of carry look ahead, because the whole idea of carrying ahead or carry look ahead or carry looking ahead, okay, so all of those ways to turn carry look ahead into a now, carrying ahead, carry looking ahead, or carry look aheading. We need to ask an English professor which way is the right way. And then the English professor is going to they're all wrong. They're all wrong, man. Anyway, so what we need is the last one, okay? Because I distinctly remember that I mentioned the last one is the most important one because otherwise, why do I even bother with the derivation? So that's this is the equation that I need. So I'm going to take another screenshot, shift, print screen, and just take this thing here and open it with fair and then move it to, come on, move to a corner like that, and then switch back to Logisim. All right. Oh, I forgot one thing, didn't I? I forgot to make it always on top. There we go. All right, so now I just have to kind of code this in. This time I need two AND gates, so I'm going to pull two AND gates. I need both of these to be in the narrow format, so we'll just kind of do it together. One is going to need two inputs, and the other one is going to need three inputs. So at this point, it is mostly just kind of tedium or chore, because I got most of it already done. So in this case, we need G1 to go to the OR gate directly. So this is G1. And once again, I forgot to put an OR gate here. Well, there we go. OR gate, narrow, and three inputs. It has three inputs because we have G1 as one input, the output of P1, G0 as another input, and the output of P1, P0, K0 as the third input. So this part is easy. Just kind of hook up these. And this is now K2. Let's change the name to reflect what it is. All right, so now it's just a matter of, how do we wire this thing up? So I'll just go ahead and wire this one up directly. And then we have P1G0. P1G0 is, we can do it up here because P1 is right here and G0 is right here. So they kind of, it kind of works out because they're physically, close. There's proximity. And then we have P1, P0, K0. Now that one's going to look a little bit ugly because I have to put the other gate down here. And I did not think about this. I did not think it through, did I? But that's okay. It just looks ugly. It will still work. There we go. And then here's P1. This is P1 right there. So we got P0, we got P1, and then we also need K0. And then we attach this to the last input of the OR gate. And now we have K2 done. All right, yep, go ahead.
I don't remember. I think you said in the lab P, G, and K0 need to be in that order. If we did G, P, and then K0 and then switched it around, like when we connected it later.
You could do it that way.
Okay. Because like that might have made it neater, but I was like too scared to do that.
Yeah, if you flip the order when you're creating the circuit, then the pins in the appearance is also going to be in the wrong order. You can fix that later on. It's just that you have to remember to do it. Yeah, because all of these pins, you can move them around, so you can actually just kind of switch them around later on. All right, so with this one, I'm just going to label K2. Oh, might as well. I mean, just P, G, K0. And just move these things into the right place. I'm not sure whether I can copy and paste, the labeling like this from the other picture. I don't think that's a good idea. So I'm just going to do this right there. Done. And now we add K3, which is the most tedious of the three subcircuits. So once again, I look at K2 and I just go like, okay, let's copy and paste and then just get rid of the stuff that I don't really need. In K3, oh, there we go. There we go. So once again, you'll remove a bunch of stuff that I don't really need. I think I can do that. Yep. That. All right. And obviously, this is the wrong equation. So let's switch back to here and pick out the right equation. You can probably figure out that this is, at this point, it's just, tedium because, it's not going to be that much different from the other one. It's just, a little more chore. So always on top, there we go. And then switch back to Logisim, and now we just need to, hook up, all these stuff. So with this one, we need 3 AND gates and 1 OR gate. So 1, 2, 3, and here's the OR. So this time I can resize all of them at the same time. So we can change all of these to narrow. And we'll just kind of change the input to, let's see, I think 4 is 1, 2, 3, 4. Yeah, 4 is probably a good one. I still have to custom change, some of the other ones, but that's okay. We can deal with that later. All right, so this one is going to have 3 inputs, and then this one here is going to have 2 inputs. All right. All right, so if I want this to look nice, we have G2 going straight into one of the inputs. So this is G2, and that can go right there. Okay, that's kind of cool. We need P2G1, and then we have P2P1G0. So the one that has 2 input and the one that has 3 input kind of need to go here, and then the one that has 4 inputs, I would probably want it to stay down there. I mean, just, from the perspective of making it look nicer. All right, so K0 can go into one of these, and then we also need P2, P1, P0. All right, so now I need to kind of think about this a little bit more and make it more systematic. So we'll just stash this one over here, stash this one down here, and then stash this one all the way down here. So that takes care of P2, P1, P0, K0 as a conjunction. And then the output of this conjunction goes into the last input of the OR gate. And then the one that has 3 inputs will need P2, P1, and then G0. So, okay, that works out, right? So here's G0. We also need P1. This is P1. So P1 is tapped here to go here. And then we also need P2, which is this one that goes from here to here. So we got P2, P1, G0, and then the first one, the first AND gate, the one that only has 2 inputs, needs P2 and G1. So here's G1, and here's P2. Okay, so P2 is going to go from here to here, and then G1 is going to go from here all the way up here, and then end up over there. There we go. All right. So at this point, I can test the circuit. The test driver was also provided along with the lab, because I'm going to give this one to all of you in case you want to use this as your solution. So I'm going to have to test it because I don't want to give you something that doesn't work and then leading you not to get all the points that you can get out of today's lab. So I'm going to test it. So that means I have to save the file first. And the best way to test your circuit is to save the file using the name that I need to save it as. So in this case, it would be 3x3ca for carry look ahead. I don't even know what the A is for.
Ahead, I'm guessing.
Ahead. Carry look ahead. So there's supposed to be an L somewhere. CLA would be better, but CA is the name that I need to refer to, from the perspective of the test driver. So I'm gonna save it like that. That too. Or Canada. Cambodia. Yep. All right. So we're gonna switch to the text tool, right here, and we need to download the test driver too. So let me go get the test driver first. The test driver, okay, let me see, where is my, right there. So the test driver, there's a link to the test driver, I think in part 1. I think so. I mean, we'll see.
I think it's one of the quiz questions. I think it's the last one.
Yeah, I think it's the last one. Yep, so I go for a preview and go all the way to the last one. Oh, yep. It's a spacer. I think it's the one that doesn't actually have a score. It's a description. There we go. And several people asked me what to do with this. Download, do not open. How do we download? I was actually surprised that of all people, you guys, some of you guys asked me how to do this, because I was thinking all of you are really proficient with browsers because you guys grew up with technology. Whereas, I grew up with, terminals and modems that you guys have not ever seen. You might have heard your grandparents talking about it. So it's right-click, okay? Right-click and then save link as. It depends on your browser. Different browsers, would kind of call it differently. All right, so I'm going to put it into CISP310, into this folder. Just, if you put everything into the same folder, it makes it easier to run the command line thing. So I click save, and now we can go ahead and run this command. But since I already named my circuit 3x3ca.circ, I can just use the simplified version here without having to use a substitute or -sub. So now we go to the command line, and I can now get out of the Logisim, the GUI version of Logisim. So I'm going to exit from here. And I can run everything from the temp folder too. I mean, it's just a matter of, it makes it kind of ugly because now I have to go to my root folder, CISP310, and the file that I need to run is test driver. So when I do this, it's going to ask me, where am I going to find 3x3ca, because it's not in the current folder. But that's okay, because, oh, okay, never mind. It's running in GUI mode because I forgot the -tty table. So -tty table makes Logisim to run not in GUI mode, but in command line interface mode, CLI mode. And it ran. Oh, okay, it ran just fine. Okay, fine. So now the question is this output what I really want? Well, instead of just visually comparing, I'm going to capture the output of the CLI mode of running Logisim into a file. So I'm going to call this 3x3ca.log. Okay, that's just a typical way for me to name something. This is the output of the log, and if I switch back to here, there is a sample output, the correct output. So right-click again, go to Save Link As, and then this time it saves it as test driver 3x3ca.log. I'm putting it into the same folder. Okay, that's fine. Click Save. Go back to the command line here because I'm using Linux. There may be other ways for you to compare whether two files are the same or not in Windows, but in Linux, this is the way I do it. So I just do a diff 3x3ca.log and then test driver. Well, it's not in the right file. So 3x3ca.log is here, but the other one is in my CISP310 test driver 3x3ca.log, I think. There we go. And if diff doesn't say anything, that means those two files are identical. So now I have just verified that my circuit does what it is supposed to do. It computes K1, K2, and also K3 correctly. All right, are we good so far? So I'm doing this so that you guys also get an idea of how to do it on your side. Yes, go ahead.
Sorry, mine's saying it's unable to access jar file download stuff.
Unable to access?
Let me just get the absolute password.
Okay. All right, so what I'm going to do now is I will include my solution in the announcement. So this way you guys get a copy of that too. So we'll go to new announcement, 3x3ca solution, and then just put it into the attachment. It's in my own folder, 3x3ca.circ. And I think Canvas won't let me save unless I put something here. This is the solution to the lab on Tuesday. Save. There we go. All right, so now you have a choice, okay? When we are ready to start today's lab, you can use my solution, which is verified to work, or you can use your own solution from Tuesday. So that's going to be, your choice, okay? Choose however you want to do it. So there we go. I forgot to do one last thing, but it's probably not necessary because I think the appearance of the K3 circuit is going to be right. So you might want to double check that before you use it. So if that is what that concludes, okay, binary addition. So what we are doing now is to move on to subtraction, okay? So just like the usual way that I teach this class and many of my other classes, the first thing we'll do is to do something that you should be familiar with already, which is, how do we perform multi-digit subtraction in base 10? So we're going to do just that. Let me switch to the right terminal so you can see it. And then I'm going to use Zerno and my stylus so I can just kind of write in freehand. All right, so we're going to do a subtraction, and I did write down what subtraction I wanted to use as an example. So in here, okay, let me do some checking first. That's done. And another example in base 10 is 215 minus 417. So 215, 417. Okay, there we go. All right, so we have 215, 15, minus 417. We have, this is x, this is y. So this x is also called the minuend, and the y is also called the subtrahend, subtrahend. So, with subtraction, it's kind of important to distinguish x and y because subtraction is not commutative, which means x minus y is not the same thing as y minus x. So now we have the next row that I will call Q, okay? It doesn't seem to make sense to call it Q, which is the same symbol that we used in base 2, because in base 10, the row Q is not computed the same way as the Q row in addition. Okay, so just bear with me right now. This is D for difference. So what we're going to do is to look at the Q row, because Q is still supposed to be the single digit something, but this time instead of single digit sum, it is the single digit difference. Okay, so 5 minus 7 has a single digit difference of, we talked about this the other day already, just want to see if you guys remember, not 2. So if you want to take 7 from 5, you go like, well, that cannot happen unless you borrow, right? So when you borrow, you're borrowing a 10. So the 5 becomes 15. So 15 minus 7 does have a single digit of 8. Okay? And then 1 minus 1 has a single digit difference of 0. 2 minus 4, once again, is 2 is less than 4, so we have to borrow. But every time you borrow, you're borrowing a 10 because this is base 10 multi-digit subtraction. So once you borrow a 10, the 2 becomes a 12. 12 minus 4 is also an 8, like so. So now we have to figure out the borrow bits. T0, in this case, can be assumed to be 0. So now I need to figure out T1. So if I look at T1, the x minus y, x0 minus y0 can contribute a borrow. So can Q0 minus T0 that can potentially contribute a borrow as well. So in this case, this is contributing a borrow because 5 is less than 7. So I need to borrow 1 from digit 1 in order to make that subtraction happen. So as a result, we have a borrow of 1 as T1. So now we want to figure out what is T2. T2 is this little spot here. So T2 also depends on the subtraction of x1 minus y1, but in this case, x1 minus y1 does not result in a borrow because x1 is not less than y1, and as a result, there's no borrow from that particular single-digit subtraction. But if you look at Q1 minus T1, we do end up with a borrow because Q1 is a 0 and then T1 is a 1. 0 is less than 1, so we need to borrow. So this time, if I want to indicate where the borrow is coming from, it's from that subtraction. But in return, we still end up with a 1 over here. So now we look at this and go like, okay, what about T3? Okay, T3 is the overall borrow of the entire subtraction, which is supposed to go here. So with this one, we have the x2 minus y2 given us a borrow of 1. So if I were to highlight it, this is yielding a borrow of 1 that I'm going to put here. So now I can actually try to figure out the D digits. So the D digits would be the single digit subdifference again, but this time it is Q something minus the T something is the single digit difference between those two. So we have 8 minus 0, which is just 8. We have 0 minus 1, which is a 9. Single digit difference is going to be a 9 here. And then 8 minus 1 is going to be a 7 over here. So that would be the final answer. And before someone says, it doesn't make any sense because 215 is less than 417, the result should not be positive. Just remember, we have an overall borrow here of 1. But what is that 1 representing? It's 1 of what? 1,000, that's right. So we are owing 1,000, even though we have $798 in the pocket. I am owing, some loan shark $1,000. So my net worth is still in the negative. Is that okay?
Yeah.
All right. Yep.
Why did we subtract the 1? Like there's like that 1 hanging to the left-hand side.
Because that's how multi-digit adding and subtraction is supposed to work. The width of the difference should be the same as xy, and then there's 1 left over borrow, or carry in the case of addition, that's just kind of hanging over here, which is of significance later on. So right now it's just kind of hanging there. Doesn't seem to be very significant. Sorry?
It kind of sucks right now. It doesn't do anything right now.
Yep. So what we're going to do next is to look at this and go like, okay, so how do we compute the Q? So I'll go ahead and just write down here. Now all of this stuff here is in the notes already. So Q of I, that doesn't, it just takes a long time to show up. So instead of doing that, I'm switching back to Joplin because I got everything typed up already in Joplin. So in Joplin, we basically have R of ij as a single digit difference is 10 plus I minus j, and then the whole thing mod 10. The reason why I'm adding 10 to I first is just in case I is less than j. Okay, just in case. But somebody may say, but what if I is not less than j? What if I is 2 and then j is 1? Then you have 2 minus 1, but you're still adding 10 to it, so you end up with 11, which cannot be a single digit because 11 as a quantity is more than or equal to 10. But that's okay. That's why I have a mod 10 at the end to make sure that I do end up with a single digit. What about the borrow function, b of ij? So b of ij is really easy because if the single digit I is less than the single digit j, then I return true because we do need to borrow from the next column. Otherwise, we return false because we do not need to borrow. So that's how your R and B are defined. R is the single digit difference, and then the borrow is B. So R is analogous to the R in addition, the single digit sum, and then B is analogous to the carry function to determine whether we have a carry to the next column or not, except in this case, we want to determine whether we have to borrow from the next digit or not. Are we still doing okay so far with this discussion? All right. So now we have to finish the structure. So the Q bits or the Q digits are really just the single digit differences between xi and yi. That's supposed to be yi, not ji. Let me fix that. I do apologize for that. The d of I is the single digit difference between the qi and the ti. So the more complicated one is what is t of I plus 1. And once again, I forgot to put the plus 1 into the subscript. So give me a chance to fix that. There we go. So t of I plus 1 is the potential borrow that results in xi minus yi, or the borrow between qi and ki. So in the notes, I use plus because it can be addition. So the question is, can both of these be ones? In other words, can b of xi yi be a 1 and also b of qi ki also be a 1? In base 10, okay? So if you think in base 10, is it possible for both of those to be 1s? So if I go back to Zernal, the question is, can the subtraction between these two digits and the subtraction between two digits both be contributing to a borrow? Or in column 1, can the subtraction between these two digits contribute a 1 to the borrow of the next column? And also, this will also contribute a borrow to the next column. The answer is it possible or not? The answer is it is not possible, okay? So this time I'm going to give you a very informal proof of why it is not possible. So if xi minus yi is given as a borrow, that means xi has to be less than yi, right? And if xi is less than yi, what is the minimum of q? How small can q get when xi is less than yi? Q, by the way, is the single digit difference. So think of all the cases where x is less than y, okay? So we have 0 minus 1, 0 minus 2, 0 minus 3, and so on. And all the cases and in all of those cases, what is the smallest single digit difference? All right, so do you guys kind of understand what I'm asking, more or less? Okay, so let me illustrate what I mean by that. And the best way to do it is to use this tool. All right, so we have 0 minus 1 having a single digit of 9. 0 minus 2, having a single digit of 8, blah, blah, blah. And then the last one is 0 minus 9, having a single digit of 1. So it would seem to me that the smallest single digit difference is going to be just 1. But it cannot be 0. Does that make sense? So what if I tell you that the borrow bit, the t bit, cannot be more than 1 either? Then you go like, oh, so that means if there's a borrow from xi minus yi, then that cannot be a borrow from qi minus ti. Because what is qi? Qi is r of xi yi. Okay? What about the other way around? What if we end up with a borrow because we have qi minus ti contributing a borrow? Why would that guarantee that xi minus yi cannot end up with a borrow? Well, think about it. Ti can only be 0 or 1, right? So in order for qi minus ti to end up with a borrow, that means ti has to be a 1, qi has to be a 0. Does that make sense? Because if ti is a 0, that subtraction cannot possibly end up with a borrow. So if qi minus ti ends up with a borrow, that means ti has to be a 1, and then qi has to be a 0. So now you think about what we just talked about a little bit earlier. If qi is a 0, which means the single digit difference between xi and yi is 0, what does that tell you about the relationship between xi and yi? They have to be the same, exactly. So if they are the same, can we still have one being less than the other one? No. So that's the proof, right? So that is the proof right there. If qi minus ti, results in a borrow, then xi minus yi cannot possibly end up with a borrow, and vice versa. If xi minus yi ends up with a borrow, then qi minus ti cannot possibly end up with a borrow. So we can only have up to one of those two contributing a borrow of 1, which also means we can now switch from an addition to an OR. So that's basically why I put an OR here instead of an addition. So now we have just gone over all of these items. And my watch reminded me that it's time to take roll. So that's what we're going to do. All right. Which is also a kind of short break for you guys. So we're going to have, today is the 8th. So I'm going to release that and show you the answer, because otherwise you won't know what word to put in. So the word turns out to be minuend. I will write it on the whiteboard because I know somebody is going to type it up wrong. Minuend. There we go. And I'll give you some time to do it. Okay, let me give you. Can you guys do it now? Okay, I'll still give you a due date of, I don't know, maybe 10 o'clock. There we go. All right. So as you guys are doing all that, I am going back to Joplin. So we are now done with subtraction, multi-digit subtraction, and we are definitely done with the base 10 example. Yep, minuend is M-I-N-U-E-N-D, minuend. It's the value being subtracted from. All right, does anyone need any more time to do this? Or are we all done with roll taking? Looks like we are all done. Okay. All right, so we are moving on to how do we do all of this stuff in base 2? So it would seem to me, if you look at the structure of subtraction, multi-digit subtraction, the only part of that that depends on whatever base we are dealing with is right here. Okay, this is a 10 for base 10. This is also a 10 for base 10. So that seems to be the only part, right? Which also means if I want to preserve the way we perform multi-digit subtraction, but apply that to base 2, what do we do? Change the 10 to a 2. Wow. So profound. But once we do that, we end up with some really kind of interesting situation. Because I did not show it here, but I'm going to kind of do it right here. So once we change the 10 to a 2, the number of cases that we have to deal with is very limited. Because we only have R of, okay, so I will give you all the cases. R of 0, 0, R of 0, 1, R of 1, 0, and then R of 1, 1. And then for each one of these, we'll also do the C, or the borrowed, sorry, B of 0, 0, and then B of 0, 1, B of 1, 0, and then B of 1, 1. All right, so can someone, tell me what is R of 0, 0 once we change the 10 over here and also over here to 2? In other words, what is 2 plus 0 minus 0 and then the whole thing mod 2?
0.
It's going to be 0 because we end up with 2 mod 2, which is really just 0. What about B of 0, 0? In other words, if 0 is less than 0, return a 1, otherwise return a 0.
0.
It's going to be 0 too. Okay, very good. Let's look at the next one. 0, 1. So R of 0, 1 is 2 plus 0 minus 1, the whole thing mod 2, which ends up as what? 2 minus 1, which is 1 mod 2. 1 mod 2 is 1. Very good. And what about B of 0, 1? Is 0 less than 1? Yes. And as a result, we return a 1. So this is also a 1. Over here, we have 2 plus 1, which is 3, minus 0. We still end up with 3. And then 3 mod 2 is 3 mod 2 is a 1. And then over here, we are asking, is 1 less than 0? The answer is no, it is false, so we return a 0 when we evaluate the B function. So this is a 1. Nope, sorry, 0. And then the last one is, what if we have 2 plus 1, which is 3, minus 1, we get 2, and then mod 2 with 2, that's going to be 2 mod 2 is 0. And then on the other side, we have 1 being less than 1. Is that true? Nope. So we return false, which is a 0. All right. So once again, not surprisingly, the result of all the possible combinations of R and all the possible combinations for B, they are all 0s and 1s. It's not surprising because the borrow has to be 0 or 1 regardless of the base, because you can only have up to 1 when you're borrowing. But for the R to be 0 or 1 is not surprising because that's why it's called a single digit blah in addition or subtraction. Okay, so the one thing we've noticed about this is, attack, that R thing, that looks like something we have seen before.
XOR?
Exclusive OR, because as it turns out, the single digit sum in base 2 is exactly the same as the single digit difference in base 2. So it doesn't matter, it just turns out to be like that. So that means, oh, okay, we already know how to deal with this, because R of ij is just I exclusive OR with j. We know that one already, not a problem. It's the borrow that is a little bit tricky, because the borrow is still only having a 1 of all the rows, but the row is no longer when we have a B of 1, 1, because C of 1, 1 is a 1, but in this case, B of 0, 1 is a 1. So this particular Boolean expression will fix the problem for us. So we negate I first, and then and the negated I with j, that would also give us the correct result. Are we good so far? So it looks to me that now we have reduced everything to just Boolean operations. So that means, even though I did not give you a borrow ripple subtractor, which is analogous to the carry ripple adder, we can probably make one. Okay, it's just the circuitry is a little bit different, but other than that, it's no big deal. Is that making sense so far?
I just really wish we could use letters other than I and J for that last one.
You wish I could use what?
Different letters than I and J for that last one. Because
Why?
It's like knots and then I and then J. It just looks.
Oh, okay. Well, I can change it. I mean, which one?
Well, it'd have to change all over.
I don't want to use AB because B is the name of the function itself. So C is carry, and then D is difference. I suppose we can use
I wasn't actually
E.
really serious about it. It was just like
Nah,
they
it's
just
okay.
look very similar.
It's easy enough. There we go. Yeah, we haven't used E or F in this class for anything, so those two are still safe to use.
Got little E and then fancy F.
Mm-hmm. All right. But, they're just placeholders. I mean, that's all they are. Okay. All right. So with this, we go like, I remember, when we dealt with the adder, we have a trick called carry look ahead, which was kind of the thing that we talked about on Tuesday. And your today's lab is a continuation of that. So the question is, can we do something like that with subtraction? I'm so glad that you asked, even though you did not. I mean, some of you probably had a question in your mind already, so I appreciate that. So as it turns out, okay, this is the derivation. Go like, okay, so here we go again. This time I did not explain, how we got from one row to the next. So I'm going to verbally, describe that. From the first to the second, it has to do with how B is defined for binary numbers. So I'm converting B of xi, yi to the negation of xi and yi. And then from here to here, I'm expanding what is qi, because qi is the exclusive OR between xi and yi, which can also be expressed this way. And then from here to here, that's the mysterious thing. That's called De Morgan's Law. So don't worry about De Morgan's Law unless you have taken CISP310 also, because if you have taken CISP310, you probably should know what is De Morgan's Law. So that's De Morgan's Law going from here to here, and then from here to here is also De Morgan's Law, and then from here to here is distribution, from here to here is simplification, because this time we have not xi and yi. Between the not xi and the between the not xi and the xi, one of them has to be false. And if you have at least one thing in a conjunction that is false, the entire conjunction is false. So that's why this part reduces to a 0, and this part also reduces to a 0. And then we have identity, because if you say anything or false, it is just the anything. So that's why the 0 disappears. And then from here to here, I introduce identity in the conjunction. So when you have a conjunction, it's always okay to say and true, because that doesn't change the value of the original expression. But you can also add additional things to a disjunction. If you have true to begin with, you can always say true or blah blah. Okay, so that doesn't change true either. So we go from here to here, and then we have distribution, and then after that I have this is based on commutative law, I think, because I just moved the items around a little bit. This thing became here, this thing became over here. That's commutative because we are moving things around. And then from here to here, we are using factoring, because both of these terms have ti in it. So we are extracting the ti, and then we are resulting in the other components. And then same thing over here. And then from here to here, we have another factoring, because not xi is common to both of those. So we extract that one, and then it's the same, similar over here. And then from here to here, it is simplification again, because x, yi, or not yi is always true, because one of them has to be true, and you just need one of them to be true for the entire disjunction to be true. So the one is simplified away because it is the identity of conjunction, because anytime you have a whole bunch of ands, just saying that whole thing and true doesn't change anything, so we can remove the and true. So that's why the ones go away. And then from here to here, it is factoring again, because both of them have ti as a component. So I extracted the ti out. So we end up with just x, not xi or yi. Okay, there we go. Boolean algebra. I'm just going to turn off my notification. There we go. All right. So once again, you are not going to be asked to do the derivation. Okay, so don't worry if you just kind of have no idea what I just said, okay, in the past 5 minutes or so. But I can almost guarantee you, what I said earlier is going to come in handy at some point of your studying at a college or university, okay, because Boolean algebra is actually critical to computer science, okay? It's just a matter of in which class do you actually have to learn it, because there will be an exam or a quiz, asking you about it. In this class, there's none, okay? But at some point, you are going to be asked, how to do these derivations. All right, so at this point here, we are not solving the problem because t of I plus 1 still depends on t of I. But you can see the format has changed a little bit because we have isolated t of I to depend on something that only depends on xi, yi, and then something else that also depends on xi, yi, and the t of I. So the linear dependency is still there. It's just that we have changed the format to a point where it is easy to fix now. So now, this time, I'm also defining g of I and p of I, but this is a redefinition because this is different. Because in addition, the xi is not negated, and also in addition, the pi is also not negating the xi. But this is the only difference, because all I wanted to do is to say this thing here becomes g of I, and then this thing that we are anding with t of I becomes p of I. That's all I wanted to do. So once I use g of I and p of I ended up with something that looks like this. T of I plus 1 is g of I or p of I and t of I. Wait, that sounds awfully familiar.
It's just the addition formula.
Exactly. Except the other one says k of I plus 1 is g of I or p of I and k of I. This one is just substituting k with t, and we have this equation here. So if in your mind you're following my statement and go like, yeah, I can see how this is really, really similar to something that we talked about already with addition. Well, that's a good thing, okay? Because you're noticing the similarity, and at least you're paying attention in class, which is good. So with that, you go like, well, doesn't that mean that we can use the same trick that we used before, so that we can remove the dependency of t of I from the calculation of t of I plus 1? The answer is yes. It's going to be exactly the same trick. It's by expansion and substitution. So that means we arrive to the same conclusion. The generator is going to look exactly the same. The only difference is when we used to have k, it is now t. That's the only difference. Are we doing okay so far? This is the end of binary subtraction, because at this point, the only difference is whether we negate x of I or not. Does that make sense? Because in the end, what is the only difference between the way we perform addition and the way we perform subtraction? It has to do with how g of I and p of I are defined. If we negate x first, it is for subtraction. If we do not negate x first, it is for addition. That is the only difference. Okay, I can see you guys are not too excited about this, but I am. Because now you can make one single circuitry that can both add and subtract, because there's a way to specify whether to negate something or not using one extra input pin. So you have one extra input pin that determines, are we adding or are we subtracting? And then the rest of the circuit, using the quote unquote look ahead mechanism, is identical. Structurally, they are identical. Did you have a question? Yep. Let's do that, right? Yep, let's do that. And let me go back to the command line first. And then this time we'll just open the whole thing, but without using the command line tool. So I cannot even remember where I put it. Is it in the temp folder? Nope. It is in the CISP310 folder. There we go. And I move my Logisim to here. All right. So the only thing we have to change is in this picture of how we computed P and G. Now, because Logisim is really nice, from the perspective of we can negate just one end of the 2 pins. So we can now say, yeah, let's negate the top, which is the X. And with this one, same thing. Let's negate the top. And now we have a subtractor. That's it. Now, if this is not cool, I don't know what is. All of that discussion of addition, subtraction, single digit thing, blah blah blah, all boils down to, wow, it's just whether we negate X first or not is going to turn an adder into a subtractor. Now I'm not gonna save this change because CA stands for carry look ahead adder. Now I remember what the A is for, adder. So I'm using carry look ahead as one word, and then the adder is the other one. That's why it's called CA instead of CLA, which is what most literature refer to as the abbreviation, is CLA. And in this case, it is not a Mercedes. Are we good so far? That's binary subtraction. So why do we need binary subtraction? Well, there are several reasons. So I do want to show you where we are now, in terms of our notes, and also, where we are now in terms of the class. What is going to be the next topic? So I do have to say that, this class does move at a pretty fast pace because that is what is needed in order to cover all the material that I want to, cover. So the next topic, this is what you're going to do today, which is part 2 of what we did on the other day. So I'm going to release that. We are now done with binary subtraction. Woohoo! Yes? Yep. So what I want to do is to show you a question that I usually ask, for the first exam, so I can give you a head start so that you can start to think about it, like way ahead of time. I already told you, I think I might have told you a little bit about the nature of that question, Sudoku, right? So I just basically look at a binary subtraction thing, remove as many digits as I possibly can, give you the least number of zeros and ones, and then you have to figure out backwards of what the other digits are supposed to be. So let me look up, the all that stuff, so I can give you an example of what I'm talking about. And 1 1 1 2 2 3. Okay, that will work. And of course, it has to open in a. Okay, that's fine. Copy and paste here. There we go. All right, so this is just a sample exam, of exam one from spring 2022. So that's just last semester. And this is what it looks like. So I give you all the question marks. Now, don't worry about the O, and the L just yet. Okay, we'll talk about those. But that's the format. You're going to look at this and go like, okay, so how do we figure out all of the question marks? And I can guarantee you that every single question mark can only be a 1 or a 0, it cannot be both. In other words, given the bits that I'm giving you, it is fully resolvable. All right? So I want you to start thinking about this, okay? Even though at this point we don't have enough, information to get started with this, not yet, because I still have to talk about what is the O flag and also what is the L flag. So that's kind of the next thing we have to talk about, because I do want to give you a focus of what kind of things I would want you to resolve in the next exam before we actually continue to talk about those particular topics. So if we move down to the next topic down the list, the next one is called binary number subtraction, and then we have subtraction and compare. That's a lab. So where is my comparison? It's right here. Then we have signed value representation, but it's also obsolete. So we have signed versus unsigned integer representation. So let me just kind of get rid of the ones that is no longer relevant. So these two are no longer relevant, but we do have signed versus unsigned integer representation and also binary comparison. So binary comparison is basically saying, how do we compare two values? As it turns out, the way we compare two values and come up with a conclusion of whether the first number is less than the second number is subtraction. So that's why subtraction is so important, because it not only tells us what the differences is between two numbers, but it will also be able to tell us whether the first one is less than the second one. Okay? So before we get there, we have to get to signed versus unsigned representation. We have 5 minutes left-ish, of this lecture, but I do want to show you, this is what you're supposed to be reading over the weekend. Okay, it is really important that you read the material over the weekend, because otherwise, things will start to stack up to the point where, things will start to, people won't understand the content anymore. All right, so we'll start with finite bit width, okay, which basically means, in math, the set of all integers has an infinite number of elements. So if you go to any math class and you ask the professor, how many integers do we have in the set of all integers? Your professor is going to say, well, there's an infinite number of integers, which makes sense, right? But in computer science, it's not. So if you're talking about a 16-bit integer, there are only 2 to the power 16 values that you can represent, because you're given a fixed number of digits. Now, to understand how this translates from base 10, it's easy. If I give you 3 digits in base 10, how many unique values can I represent? The smallest one is going to be 0, 0, 0, right? The largest one is going to be 999, which is 999. So between those two, we have 1,000 possible values, because 0 is its own value, right? So we count from 0 as one value. So by the time we get to 999, we end up with 1,000 values that we can represent. So it is the base to the power of the number of digits. That will give you the total number of values that can be represented. Does that make sense? So when we translate that base 10 observation to base 2, it's the same thing. Base 2 means the base is 2, and then the number of digits typically is going to be 8 for a byte, 16 for what we call a short word, 32 bits for, I cannot even remember how that's called these days, and the 64-bit is the most common width for integers. So that means with a 64-bit integer, we can represent 2 to the power of 64 unique values. That's a lot, but it's not infinite. That's the thing, is it is not infinite. And then the second question is, how do we represent negative values, which is going to be the more kind of tricky one. So the next thing we, in section 1.1, we look into modulo arithmetic. So modulo arithmetic is basically establishing what we call equivalency in a certain base. So we say A is equivalent to B mod n, means, this is the notation. And then this is, basically the more general equation. So there's a Wikipedia page on all of this stuff here, because okay. So the best way to look at this, okay, I'm going to switch back to my tablet. All right, so there's this, and then I need to switch on my side so I can actually draw on it. There we go. All right, so imagine, let's only focus on 2 bits, okay? So we, instead of a number line, now we have a number circle. So the number circle goes like this, okay? There are 4 slots because 2 to the power of 2 is 4. So we're looking at 2-bit integers right now. And we can now say, okay, so let this one represent 0. This is going to 0, 0, 0, 1, 1, 0, and 1, 1. I think everybody can agree that given 2 bits, these are the 4 possible permutations of the zeros and ones, right? So the question is, which one is going to represent which value? Okay, the first 4 is easy, because the first 4 goes like this. I'm going to change the color to dark green. We can say, oh, okay, let this one represent the value of 0. It makes perfect sense, because in this case, we have none of 1 and none of 2. So we have 0 plus 0, which is 0. Okay, that makes sense. We'll use this one to represent the value of 1, which also makes sense, because we have 1 of 1 and none of 2. So we have 1 plus 0, which is 1. How about this one here? What about the bottom? What value do you think it should be representing?
2.
2, okay, very good. And then we have 3 on this side, right? There we go. So modulo arithmetic basically says, if I really have to represent 4, this is where 4 is going to go. This is where 5 is going to go. This is where 6 is going to go. This is where 7 is going to go. And like so, 8, 9, 10, 11, and so on. So it just goes round and round and round. So now we ask the question of, Tech, do you mean 0 and 4 are the same? No, that is not what I said. I'm simply saying that in modulo arithmetics, they are congruent. So there's that magic word of congruent, because it is kind of like equivalency, but in a very special way. Question?
Is that saying that like the last 2 bits in the representation of those values will end in that specific little sequence? So like
Right.
9 will end in 0, 1.
Yep.
10 will end in 1, 0.
Yep.
Ironically.
Yep.
11 will end in, sorry, that is 11. Okay, 11 will also end in 11? Yeah.
Yes, 11 ends up at 1, 1.
Sorry.
That's base 2,
Yeah,
this is
1, 1,
base
yeah,
10.
sorry.
Sorry.
11 ends up in 1, 1.
Yep. So, what about negative values? Because I want to leave that note before I end this lecture is, what about negative values? Because in normal arithmetics, all we can do, we can do something simple. Like, for instance, if I have 29 and I want to express the negative quantity of 29, I just put a little sign here and say it is on the other side of 0. Okay, that's pretty easy. But when you only have zeros and ones, it's a little bit different. Because when all you have are zeros and ones, how are you going to represent negative values? So one thing we want to look at this is now we change to the red color. If going in clockwise direction is incrementing, it kind of makes sense that going in counterclockwise direction is subtracting, right? So now we can say, all right, so this one can also represent -1. This one can also represent -2, -3, -4, and so on. So now we are now looking at this number wheel, and say, oh, so that means -1 and 3 are congruent. Okay, they are considered equivalent when we perform mod 4 calculations. If everything is mod 4, then these two are having the same representation. -2 and +2 are also congruent. Okay, so we're getting into congruency, yeah, which is a interesting but not really difficult math concept. So that's what 1.1 is trying to address. Is now we're dealing with fixed width bit patterns, and as a result, we are saying, well, with all the integer values, some of those values, many of those values, will basically share the same representation. So now the question is, why is this even important? Why is congruent modulo an important concept? And the reason why it is important is illustrated by this thing here, because in the end, okay, I need to finish this lecture by indicating which values turn out to be actually useful. So as it turns out, 0, 1, 2, 3. Those are useful, because they are the unsigned values that you can represent when you're only given 2 bits. Okay? On the other hand, let me use orange here. If you're using signed representation, then you should still be able to represent 0. So 0 is still 0, using the signed representation. 1 is still 1 using the signed representation. But then -1 becomes the value being represented by 1, 1. And then 1, 0 is used to represent the value of -2. So when you look at the orange circles or the orange squares, they are indicating how to interpret a particular bit pattern. And we can see that in the signed interpretation, we are interpreting 0, 0 as 0, 0, 1 as 1, but 1, 0 is now interpreted as the value of -2, and 1, 1 is now being interpreted as the value of -1. It is just interpretation. So the best way to illustrate, what interpretation is really just to look at this thing here, which is -29, because if you use a microscope and go all the way down to the pigment, okay, and you look at the individual molecules of the pigment, does that pigment molecule tell you what is being represented? The answer is no, okay? It's only you looking at the pigment from where you are standing and understanding the symbols that you're interpreting the specific pigment distribution like this as the value of -29. It's an interpretation. So this is the same thing. -1 being represented by 1, 1, as 2 bits is the same thing. You look at the bits and go like, okay, I see this transistor has a high voltage. That transistor also has a high voltage. Okay, together, they are now representing the value of -1. So we're going to get into this discussion a little bit more and also get into what is congruent modulo on next Tuesday. But it is extremely important that you guys read ahead of me because this entire discussion is very math oriented. And as a result, getting familiarized with the concept is also important because as you can see, there's a whole bunch of math stuff here. And then, we talk about how we figure out the bit pattern of a particular negative value, which is called 2's complement. So this is going to be the module that we'll be talking about on next Tuesday. So this is something that you should probably read over the weekend. So are we okay so far? Yep, okay. So now it's time to get you guys started with the assignment. The lab for today. I think, okay, there we go. So I'm going to expose these two, and they will be due at the usual time of, I'll give you guys up to 11:55. But you should be able to see it now and actually do it now. The access code is 3x3b, not part 2. So 3x3b is the access code. All right. And it's due at 11:55. I'll give you up to that. 5 more minutes. There we go. Save. And then you also have to turn in the file, just like with the previous one. That's also going to be due at 11:55. So this one. I think this lab should not take as long as the previous one, but there's one little trick to this lab that most people or many people, step on, that little trick, the little landmine. It has to do with, you have to remember how to compute the sum bits, okay? So I'll just write it here, S of I equals to what, okay? Because that's, a lot of people forget this one, and they move things over by 1 bit, okay, making things not work. But make sure that you remember how S of I is defined. All right, that's that, and I'm going to stop my OBS streaming.